Well, the topic that I'm going to take today is the effect of source impedance on the performance of converters. As of now, we have discussed various converters, and during that discussion, we studied the effect of the resistance and inductance on the load side. But in this topic we will be discussing the effect of source impedance on the performance of the converter. How the source impedance affects the performance in terms of the voltage and current waveforms, the average voltage, and the similar parameters. How source impedance can affect it. Now, first it is important to understand what is source impedance and why it is caused. In most of the cases, you might have seen the converters are supplied through the transformers. And let us say if a converter is supplied with a transformer, that transformer will have some inductance in it. That transformer will have some resistance in it. So the resistance and inductance of the transformer, which is called the impedance, will be creating an effect on the performance of the converter because the transformer here will be considered as the source. Now, this source is having some impedance, which includes the resistance and the inductance as well. So let us see what happens if the impedance is only a pure resistance, and then in the preceding part we'll discuss what if the impedance is purely inductive. So let us see if the source impedance is resistive, then what will happen. Resistance, what does it do? Resistance has an effect on playing with the magnitude of the current. So if the resistance is present in the source, then it is going to reduce the voltage by introducing a small voltage drop. So that means if there is resistance in the source, the average output voltage of the converter will reduce, and it will reduce by this factor I naught into Rs. Now what is I naught? I naught is the current that is flowing through the converter, or you simply call it constant DC load current, and Rs is the resistance of the source. But this resistance here is taken as per phase. So that is why if it is a single phase converter, we will say that the drop in the converter is equal to I naught into Rs. But if it is a three-phase converter, in a three-phase converter at a time, two phases work together. So these two phases will bring you a loss of 2 I naught into Rs. So idea is the resistance can only reduce the magnitude of the voltage. Why? Because it is creating a voltage drop. But if there is but if there is inductance in the source, then what will happen? So in next discussion, let us see if the source impedance is taken as purely inductive. Here the load inductance that we are considering is assumed to be very large, so that the output current is constant. So this is our first assumption. Please note it. The first assumption is that the load inductance is such high that the output current, that the load current is very constant. Now let's see the pattern. Earlier, when the load inductance was not there, let us say it is 0. The value of Ls is 0. So if it is 0, what will be the way of working of this converter? This is the source Vs. When T1 and T2 are triggered, this source gets connected to the load through T1 and T2. So basically, when T1 and T2 are triggered, this forms a series circuit consisting of Vs, then T1, then load, then T2, and then back to supply. Now when T1 and T2 is conducting in a single phase full converter, at a time this combination works for 180 degree. If the alpha is kept 0, the combination will, this T1 and T2 will work for 180 degree, and for the next 180 degree T3 and T4 will conduct. And when T1 and T2 they stop conducting after 180 degree, immediately the current is transferred to T3 and T4. So whenever we discuss the converters without source inductance, we always make an assumption that as long as T1 and T2 are conducting, T3 and T4 are off, and when T1 and T2 stop conducting, the current is immediately transferred to T3 and T4. So here this sequence of conduction is shown by this. Now here it is shown that during this 180 degree T1 and T2 are conducting, and this is the point where T1 and T2, the current through T1 and T2 immediately drops to 0, and the current is immediately taken by T3 and T4. So we can call here that T1 and T2 are the outgoing thyristors and T3 and T4 are the incoming thyristors. So whenever the incoming thyristors take up, when the incoming thyristors are fired, immediately the current from the outgoing thyristors gets transferred to the incoming thyristors. But what happens when the load inductance enters? This load inductance, it has an impact on the current, because inductance is supposed to delay the current. So when this supply contains an inductance, the voltage comes first and the current gets delayed. Now because of this delay in current, what happens? The T1, T2 which were conducting, and at this point these two thyristors are supposed to go out. So rather than going out quickly, the current through T1 and T2, it falls slowly, and at the same time, because this is the point where you fired T3 and T4. So when T3 and T4 are fired, the current through T3 and T4 starts building, and the current through T1 and T2 starts dropping. So there is a time during which these four switches, they all are conducting, because the current through T1 and T2 is reducing because it has to become 0, and the current through T3 and T4 is rising because it has to take up the load current. So the transformation, the transfer of current from this combination to this combination, which was earlier considered as instant, it is not happening instant because of the presence of this inductance at the source side. Now let us see what happens if at the same time these four switches are conducting. So if these four switches are conducting at the same time, the load is said to be short circuited, and there exists a small time during which T1 and T2, the current through these two is reducing while the current through T3 and T4 is rising. So this makes a small duration during which all the switches are on, and this small period is called the commutation period. Commutation period means T1, T2 are going out and T3 and T4 are coming in. This is also called as overlap period, and during this overlap period, the average output voltage is 0. The average output voltage is 0. We'll try to understand in the coming slides. And if it is a three-phase converter, the average load voltage will be VA plus VB upon 2. I'll explain this how it is coming. And this commutation period, this is referred to as mu. Mu means it is during the time when this overlap is taking place. That angle is called the overlap angle, or mu. This may be taken in degrees or radians depending upon how you are doing the calculations. As such, the effect of source impedance is three. There are three effects. One is it lowers the mean output voltage, because as I said, during this period, during this small period of overlap, I said that the output voltage becomes 0. So if the output voltage for some duration is getting 0, the average output voltage is going to be reduced. The second effect is to distort the output voltage and current waveforms. Obviously, if the voltage which was supposed to rise and it immediately drops to 0, that means the waveform is distorted. It got distorted because of this change. And third, because the output voltage is changed, output current is changed, so obviously the performance parameters of the converter is going to be changed, is going to be modified. So these are the three effects that the source impedance, particularly the source inductance, causes on any converter. Let us see this effect in detail, and let us go through small mathematical portion, a small derivation, where I'll show what exactly happens during this time. Let us say at 0, this is the time when the input supply is given. V1 is the positive voltage, and V2 is the opposite voltage. So if V1 is Vm sin omega t, we should say that V2 is minus Vm sin omega t. Now when this voltage is given, let us say at alpha, we fire thyristors T1 and T2. So thyristor T1 and T2, they are fired at alpha. So if T1 and T2 are fired at alpha, prior to it, there were two thyristors T3 and T4 which were already conducting. Just look at this sequence. So that means if you trigger here T1 and T2, that means from this point T1 and T2 are supposed to conduct, and T3 and T4 are supposed to go at rest. Similar way, if T3 and T4 are triggered here, so at this point T1 and T2, they are supposed to go at rest, and T3 and T4, they are supposed to take over the current now. So let us examine this figure and consider that T1 and T2 are fired at this point. So when T1 and T2 are fired at this point, what happens? At this time, the assumption that we have made is I naught is constant. So if we assume that the current I naught is constant all the time, because we have considered a high value of inductance, if I naught is constant, that means the current which was supplied to I naught through T1 and T2, if the current now starts flowing through T3 and T4, the load current will not be interrupted. But during this changeover, what is happening? During this changeover, the current which was earlier flowing through, this is the part when the current was flowing through T3 and T4. So T3 and T4, the current, let us say through T3 and T4 is I2, and let us say through current through T1 and T2 is say I1. So that means at this very point when T1 and T2 are triggered, at this very point the current I1, which is the current of T1, this current is supposed to rise, while the current I2, which is the current through T3, this current is supposed to decay. Without source inductance, this crossover doesn't take place. But because of the presence of this inductance, this crossover takes place. So during this time, the current I1, it rises from 0 to I naught, and during the similar time the current I2 falls from I naught to 0, and this time from this point to this point, this time is called the overlap time, and if you express this in angle, it is called the overlap angle mu. So this angle from this point to this is called mu. So during mu, what is happening? During mu, all these switches are on. That means there is a short circuit between point this and this. So if there is a short circuit between these 2 points, that means the load is short circuited. So if the load is short circuited, that means the voltage across the source is 0, because it is short circuited. So if the load is short circuited, the voltage across it obviously will be 0. Let us see what further happens to it. We have made its for this figure A, we have made its equivalent circuit. This equivalent circuit says this is V1, which is positive. So when Vs is positive, T1 and T2 are in action. When Vs is negative, T3 and T4 are in action. So we have called the positive voltage as V1 and the negative voltage as V2. So V1, then Ls, then T1, T2, and this load. So we have, that is why I drawn it like this. So this is for the positive cycle, and for the negative cycle, it is V2, then T3, T4, and this load. So this is the second case, and this load is connected here. Now what happens at the time of overlap? At the time of overlap, this is short circuited and this is also short circuited. So if we apply the KVL in this loop, what will happen? In this loop, A, B, C, D, A. During this time, this complete circuit is a short circuited structure. Let us see what happens. If I apply the KVL during this time, what we'll get? We'll get V1 minus Ls. V1 minus Ls into di1 by dt. and this voltage will be equal to V2 minus Ls into di2 by dt, because here the current is I1, here the current is I2. So the voltage drop across it will be Ls into di1 by dt. The voltage across this will be Ls into di2 by dt. So V1 minus this drop will be equal to V2 minus this drop. It is written in this equation. So if we solve this equation for V1 and V2, we get V1 minus V2 is equal to Ls di1 by dt minus di2 by dt. And if we solve it further by entering the value of V1 as Vm sin omega t and the value of V2 as minus Vm sin omega t, this becomes V1 minus V2, this becomes Vm sin omega t minus minus of Vm sin omega t. So this gives you 2 Vm sin omega t. This becomes equal to Ls di1 by dt minus di2 by dt. So let me point this equation as equation number 1. Now we also know, we have assumed that the load current I0 is constant. If we assume this current I0 as constant, that means during this overlap period, I1 and I2 will be equal to I0. So whatever at whatever time during this duration, if you see, if you see this complete duration, during this duration, current I1 and I2 will be equal to I0, because by the rate at which this is falling, at the similar rate this is increasing. So that is why we can say that I1 plus I2 is equal to I0. And if we differentiate this equation with respect to t, we get di1 by dt plus di2 by dt equals to 0, because I0 is considered as constant. So this becomes your equation number 2. And from the previous equation, from the equation number 1, we got this. If we add these two equations, we get di1 by dt equals to Vm by Ls sin omega t. So we get this, but we are interested in knowing how this is affecting the output voltage. So let us solve it further. This current I1, let me go back to this figure. Please note that this current I1 is rising from 0 to I0. This value is 0. And this point is point alpha, because here it is triggered. So at alpha, the current I1 is 0. Whereas at alpha plus mu, this complete angle is alpha plus mu. At alpha plus mu, this current I1 is equal to I0. So that means the current I1 is rising from 0 to I0 in a duration of omega t equals to alpha plus mu. So omega t equals to alpha means the time is omega t equals to alpha. That means t is equal to alpha by omega. So here it is alpha upon omega, and this integration will be done to alpha plus mu upon omega. So if we integrate this current from 0 to I0, for this time we get I0 equals to this value. Let me put this as equation number 5. So I0 is equal to Vm, I0 equals to Vm upon omega Ls cos alpha minus cos alpha plus mu. Let us solve it further. The output voltage during this time, during the overlap period, overlap period is from alpha to alpha plus mu. During this overlap period, the voltage is 0. The output voltage is 0. So if we wish to find out the output voltage, then how will we calculate it? During this time, you can see the output voltage has started coming from this point, and this voltage, this point is alpha plus mu. From this point, the voltage is available till this point. Now what is this point? This point is pi. And what is this point? This point is pi plus alpha, because this is again alpha. So that means the output voltage is available from alpha plus mu to pi plus alpha. I repeat, the output voltage is available from alpha plus mu to pi plus alpha. So that means if we wish to find out the average output voltage, then we will integrate Vm sine omega t from alpha plus mu to pi plus alpha, and the periodic time will be pi. So if we solve it, we get it equal to Vm by pi cos alpha plus mu. Now, going further, we all know if there is no source inductance, the output voltage of a full converter is given by 2 Vm by pi cos alpha. And if alpha is kept as 0 degree, the output is 2 Vm by pi. That means this is the maximum output that we could get through a full wave converter. So for a full wave converter, the maximum output average voltage can be 2 Vm by pi. This is provided alpha is 0 and there is no source inductance. So if we write it VO maximum, so VOX, this equation can be written as VOM by 2 because it is 2 Vm by pi. So I'm writing it 2 Vm by 2 and this remains same. So if this remains same, let us go further through this equation number 5. This is equation number 5. Through this equation, let us try to get this value of cos alpha plus mu. So cos alpha plus mu from previous equation 5, it is cos alpha minus omega ls Vm upon this. Now if we substitute this value in above equation, we get, if just this value is substituted here, what do we get? We get V output as 2 Vm by pi cos alpha minus omega ls upon pi into I naught. Now just examine this equation. 2 Vm by pi, let us forget about this. This is same. This is just here, this omega is replaced by frequency. But if you examine this figure, if you examine this equation, the output voltage is 2 Vm by pi cos alpha minus omega ls upon pi into I naught. That means this is the voltage which got reduced from this, because for a converter, with full with no source inductance, if there's no source in the no source inductance in the converter side, then the output voltage was 2 Vm by pi cos alpha. But with the presence of this inductance, this is the amount omega ls by pi into I naught which got dropped. So this is a small drop that happens because of the presence of inductance. Now with this equation, we can draw this small circuit. So this is a DC equivalent circuit for this small equation. This circuit shows that 2 Vm by pi cos alpha. This battery is represented for a converter in which there is no source inductance. So for that converter, the output voltage is 2 Vm by pi cos alpha. This D is just connected to indicate that the current is unidirectional. Now this is a load. I shouldn't call it load, rather this is an impedance in which the drop is taking place, and this is equivalent to omega ls by pi. This is equivalent to omega ls by pi. So when this is the source through which, if we reduce this drop omega ls by pi into I naught, we get the output of this converter. So as we increase the current, because this output is directly proportional to these two, because this equation in this, it is minus. So sorry, I can say that this output voltage is inversely proportional to these two values, ls and I naught. So if I naught is increasing, this voltage V naught is going to reduce. Why? Because if I naught increases, the drop will increase, and this drop will reduce this current output voltage. So as high as the value of Ls, the drop is going to increase. So the source inductance may cause the voltage to reduce. Now the effect of source inductance is to present an equivalent resistance, which is given by this in series with the this we have already discussed. And as the load current increases, the commutation interval also increases. This is obvious because if this is increasing, the commutation time is going to increase. The commutation interval mu is going to increase, and more is the value of mu, lesser will be the output voltage V naught. Now this mu can be as large as pi. So if this overlapping interval is equal to pi, that means if this overlapping period is equal to pi, that means the load is permanently short circuited and the output voltage is 0. As long as this is less than pi, equation 8, this equation is valid. This equation becomes 0, the output voltage becomes 0 if mu becomes equal to pi. That means if alpha equals to 0, but the mu exists, this mu, after this mu only you are going to get the voltage. So that means alpha, for if you want to have the minimum value of alpha, the minimum value of alpha can be equal to mu. So any converter having the source inductance will be fired from mu to 180 degree. Rather mu to 180 degree, that means the firing range will be 180 minus mu. The firing range will be 180 minus mu. Rather, we take the thyristor turn off time also in calculation, because thyristor also takes some time to turn off. So the firing range becomes 180 minus pu minus delta. Now this small delta is, it represents the turn off time and the factor of safety. So this is the maximum firing range that we can have for a single phase converter with source inductance Ls.